All right, let's dive into a real mathematical mystery story. It's a tale about a problem that looks completely impossible, a secret method that cracks it wide open, and a beautifully simple solution that was hiding there the whole time.
So, here it is. This is the villain of our story, a ninth-degree polynomial equation. I mean, just look at that thing. The numbers are huge. There are terms all over the place. Just staring at it is enough to make your head spin. This isn't just a math problem, it's an absolute monster.
I'm serious, just think about it for a second. Where would you even start? Any of the standard ways of solving these would get so messy, so fast. It feels totally unsolvable, right? A real mathematical maze. So let's see how the author of our source paper did it.
To really get why the solution is so cool, you first have to appreciate the sheer scale of the challenge here. This is not your typical algebra equation. It's a completely different kind of beast. Okay, quick refresher, just so we're all on the same page. A polynomial is simply an expression with variables and coefficients, like the one we're staring at. They're one of the fundamental building blocks of math. But here's the kicker, the degree. That's the highest exponent in the equation, and in our case, it's a 9. And when you're talking about polynomials, a degree of 9 means you are dealing with a mathematical giant. Finding the roots, the values of x that make it all equal 0, is a legendary hard problem.
But the paper we're looking at doesn't even flinch. It lays out this really unique, almost elegant method for taming this monster. And it all comes down to a very specific set of information.
The entire solution hinges on these 9 values, which the author gives us right up front. And I love this metaphor. If our giant polynomial is a super complex lock with 9 different tumblers, then these values are the perfectly cut keys that are going to open it.
And here they are. These are the 9 secret keys. Now, if you're paying close attention, you might notice something kind of wild. These are the exact same numbers as the coefficients from our monster polynomial. The author's whole method is based on this incredible insight that this specific set of values holds the answer.
Okay, so we have the keys, but how do we know they actually fit the lock? Well, the author walks us through this very systematic proof. It's like we're going to turn each key one by one and listen for that click.
The process itself is surprisingly straightforward. The author uses this verification formula, one that basically tests how these keys interact with the polynomial's hidden structure, and runs the test 10 times. Once for a variable k equaling 0, then for k equal 1, k equal 2, and so on, all the way up to 9. The goal is simple. What happens every single time?
For the very first step, when k equals 0, they plug all the values in. The math behind the scenes is messy, for sure, but the result? It's astonishingly clean. It simplifies down to exactly 0. You can almost hear the click of the first tumbler falling into place. The first key works.
Next up, k equals 1. They run the whole process again. The numbers going in are different, but the pattern holds. The entire complex expression once again boils down perfectly to 0. That's the sound of another tumbler clicking into place.
Let's do just one more. For k equals 2, the calculations get even hairier, but the outcome? You guessed it, 0. The pattern is holding firm. At this point, you know something really profound is happening. This isn't a coincidence. And it just keeps going. The paper confirms it for every single step. K equals 3, 4, 5, all the way up to 9. Every single time, the complicated math just melts away, leaving a perfect 0. Every key slides into the lock. Click, 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 and the lock springs open.
So, all the keys have been turned. The proof is officially complete. But what did we unlock? Now we get to see the incredible transformation of that monster we started with. And this is the payoff. Because every single one of those tests resulted in 0, it's mathematical proof that those giant intimidating coefficients in our polynomial, they're really just an illusion. They're structured in this perfect hidden way that makes them all cancel each other out.
See, that testing process allowed the author to define a new set of coefficients. And as you can see here, that methodical proof revealed their true value. Every single one of them is 0. All that complexity, all those millions and billions, they just vanish. And this slide just says it all, doesn't it? On the left, the absolute beast we started with, and on the right, what's left after all the dust settles. The entire 10-term polynomial just collapses into one single, beautifully simple term. X to the 9th power equals 0.
And of course, the solution to that is wonderfully obvious. The only number you can raise to the 9th power to get 0 is 0. That's it.
That is the single, solitary root of our once unsolvable polynomial. All that work for such a simple answer.
So what's the big takeaway here? It's not just about solving one ridiculously tricky math problem. It's really about the beauty of the process itself.
This right here, for me, this is the core lesson. What looked like a totally chaotic mess of numbers was actually a highly structured, highly ordered system. It just needed the right method, the right key, to peel back all those layers and show the profound simplicity that was hiding underneath it all.
And that kind of leaves us with a fascinating thought, doesn't it? This puzzle wasn't solved by brute force. It was solved with insight. It really makes you wonder, what other problems out there that seem hopelessly complex are just sitting there, waiting for someone to find the right set of keys?